Okay, so as we discussed just now, so the billet itself, once you make the billet using the, and you have Thixo materials billet, you can actually use that to and machine it to make parts, but basically it won't have a good characteristics in terms of strength, fatigue, characteristics, so on and so forth. So only a small number of alloys that can be used for this particular operation. Okay? As I mentioned, so let's say, for example, for the aluminium, so these two alloys are well adapted for the Thixoforming process. So for basically the reason why this alloy because it has certain component in this alloying element. For example, the shape retention is improved by decreasing the silicon concentration with some loss in fluidity and strength. So if in aluminum alloy, in an alloy, if you want to increase the viscosity, then basically you put silicon. If you put silicon, then the viscosity will increase, but the strength will decrease. You can also put magnesium. So magnesium, basically, if you put magnesium element inside the alloy, basically the strength will increase. Strength. Uh, you can also modify the eutectic. So eutectic is basically the alloy that actually achieve the equilibrium condition. So we're talking about eutectic point is where actually the maximum percentage at the lowest temperature can be achieved for that particular material, for that particular alloy. So you can modify the eutectic by adding strontium. And it says here, so these are basically the alloy for the Thixoforming operation. The rest basically you can read on your own. So let's look at the alloy characteristic with regards to solidification, temperature range, eutectic phase, cooling rate, and also potential for aging. So we're going to go in detail a bit in terms of how to make this semi-solid slurry or Thixoform materials, Thixo materials or feedstock. So you can use it. You can make these based on the solid state or liquid state. So if it's solid state, then basically you're going to use these two the two processes that what they call it, then being used is called the stress-induced melt activating process, SIMA, or RAP, recrystallizations, and also partially melting process. If it's liquid state, then you use the magnetohydrodynamic stirring methods or cooling slope casting methods. So we're going to go through individual process briefly. So there are two solid state methods, Thixo, SIMA, and also RAP. So let's talk about the SIMA method, strain-induced melt activation methods. Okay, these techniques relies on reheating deformed materials into a semi-solid state. So you have a solid state, so you reheat the material, deform the materials into a semi-solid state. Initial deformation occurs above the recrystallization temperature, and there's a cold work at room temperature. And what this do is actually store energy flow as a result of partial remelting. So and material reaches a semi-solid state to obtain uniform and dendritic spherical solid state. So I think this you can read on your own. So I'm going to show you here. So this is the SIMA methods. So what happened is you have the melt the materials and cast, And then you extrude the materials at above the recrystallization temperature. So again, this is the solidus temperature, this is liquidus, solidus, and this is crystallization temperature. So what you do is you melt and cast. So and then you cool it down to room temperature. Then you do exclusions, and when you do this exclusion, you have to do it above the liquid crystallization temperature. So basically, the work being done uh, on the material is going to be hot work, and then quench it. So once it's quenched, then basically you do cold work. Bottom here means that you need to go through a process, quench and then cold work, and then you heat it back above the solidus line. So this is where the SSM will form, semi-solid metal will form. So So the evolutions of the dendritic microstructure during this process, during Sigma process, occur as a result of a partial remelting that is applied to the deformed material. So the deformed materials, and then when you heat it up above the solidus line, yeah, and it will uh, uh, it will basically during the cold work, all this dendritic microstructure will be broken down. And when you heat it up the solidus line, then it will form into a spherical and globular structure. So when the crystallization is achieved, and then you can energy infiltration flow to the high angle boundary grains, plus of solid particles has direct relation with the rate of heating and degree of cool work. So the size of the globular structure and particles has something to do with the rate of heating and degree of cold work. Remember the initial discussion just now when we want to form these billet materials for the Thixo billet material, Thixo slurry material. You have two objectives. One is uh, you want to convert the dendritic structure into spherical or globalized structure. The second is you want to have a fine structure. You want to have a fine structure. So the fine structure is the size of the structure, grain size is basically controlled by the uh, rate of heating and also degree of cold work. So basically, you have to depends on different materials. Then you have to look at the rate of heating, also how much cold work you have to do on the materials to convert it into a good Thixo material. Uh, the prep, recrystallizations and partial melting is similar to SIMA, but essentially the difference is at the initial deformation occurs below the recrystallization temperature, that is during cold work. So if you look at the SIMA, so it starts with a molten metal, you pull it down, and then you do not hot extrusion but warm extrusion process. So you have to do the work, the extrusion, which is the work on the material, the deformations on the material below the recrystallization temperature. For the SIMA, this happen above the recrystallization temperature. So that's basically the main difference between the two, between REM and SIMA. Occurs as a result of high energy liquid metal flow through high angle grain boundaries to obtain fine non-dendritic microstructure. Utilize the cold work to warm work at the temperature below the recrystallization temperature to ensure maximum steam hardening. So the heat is induced in here due to the work being done on the material. Uh, uh, But it must be done below the crystallization temperature. The reason being is you want to ensure maximum strain hardening. So when you do maximum strain hardening here, basically what you do is that you break down all this dendritic structure into a spherical structure. Um, of course, effective application, you need to control the parameters. What parameters? Duration of the heating, creating temperature, amount of plastic deformation, so on and so forth. Any questions? So, so in the to make the pellet for the Thixoforming process, you have you can do it in solid state. In under solid state, you have a sigma and you have rep. Basically, the difference between the two, the plastic deformations that happen, the initial plastic deformation that happen for sigma is above the uh, recrystallization temperature, but for rep is below. So that's a difference. So if you want, so there's another methods to make a raw materials using liquid state methods. And this liquid state method, there are two methods. One is magnetohydrodynamic stirring, MHD. The other one is they call it by mechanical means by slope casting. MHD tank is based on the fundamental law of electromagnetism, magnetic field. So you can read this: magnetic field, the electric current intersect in the liquid, their repulsive intersect propels the liquid into direction perpendicular to the field of the current. So this is what stir the liquid. So if you look at the lab I mentioned just now, you can see people put a container on the apparatus, and inside it you have a liquid, and the liquid stir by itself, that's due to this particular phenomena. Is when we have magnetic field and electrical intersect, and then basically it propel the liquid through the move. So in this process, the dynamic electromagnetic field is applied to the metal near freezing. So for this particular case, at the liquid state, so as it's cooled down, then you apply this. So when this is being applied to the material, then basically it's going to stir the molten metal, right? And it will generate a high local shear. So basically there'll be a shearing happening inside the material itself. So because of the shearing, basically all the structure will not be able to form because of the shear, right? So it's broken down. So as a result, then you have a fine uniform size, typically 30 microns. Solid particles are produced. Right? So this is the structure. Looking at the structure, so this is as you go into the stirring. So at the end of it, you can get a spherical columnar globular structure. The other method is called cooling slope casting. Cooling slope casting. So cooling slope casting is quite a simple process actually. So basically, what you do, you pour a metal with suitable superheat temperature through a cooling slope plate into a mold. So basically, what you do is you melt a material into a certain temperature. It depends on the alloy, and pour it through a slope. So you of materials that's in the slope. So the metal will move down the slope into the mold. So this will provide a globular or spherical microstructure when heated to the semi-solid temperature. So the reason why this happened is basically the dendritic fragmentation. So during when the materials move down the slope, right, as it's solidified, basically this dendritic structure will get fragmentation. fragmented,
What will
broken down. So as it's broken down, then it's formed globular spherical material. The fragmentations of the weak dendrite arms may occur near the contact surface of the cooling slope. Samples, because there are the crystals in the partially solid but not collide under gravitational force of the inclined cooling slope. So this is the examples of it. So first you have to mold the metal, right, to a certain superheat temperature. So this is the cooling slope. So there's a water going to a cooling slope to cool the materials. And then once done, then basically you pour the molten metal into that particular cooling slope. So as this material moves down, as it's cooled, the dendritic formations on the cooling slope will be broken down. Fragmented, and basically the result you can have a spherical and globalized structure of a pellet in the mold. So this will be your billet. Okay. Any questions? Okay, so basically, that's the first stage of the Thixoforming process, which is you have to make the billet. So to make the billet, there are two ways. One is using solid method, the other one is using liquid method. So we have to look at the four techniques to make the billet. So the second stage is basically you have the feedstock ready, you have the billet ready. Now you have to reheat it. So that's the second stage. Um, so so this is a critical stage of the Thixoforming process. The purpose is to obtain desirable nominal liquid fractions, but to ensure transformations of the solid phase to spherical morphology with a fine particle. So the purpose of this particular stage is basically you want to obtain desirable nominal liquid fractions. Just now mentioned initially, you want to have about 30 to 50% liquid fractions for during the Thixoforming process. So to achieve these liquid fractions, basically you have to reheat the material. Reductions of the driving force of such morphological evolutions in a semi-solid state is the reductions of interfacial energy between the solid and liquid phase. So once you heat it up, then you reduce the interfacial energy between the solid and liquid phase. So to achieve this semi-solid state, important processing parameter during the heating process include the accuracy, uniformity of the heating temperature and heating duration. So temperature and durations of heating need to be controlled very well. So you have to do characterizations and optimizations in the process to make sure that you can achieve a certain liquid fraction, maybe 30% up to 50%. Then based on that, then basically you determine what's the temperature and heating duration. So if you heat too high, then you cause instability of the slug, resulting in difficult for slug handling. So basically, if temperature is too high, then basically you're going to have too much liquid. If you have too much liquid in the liquid phase, then basically it's going to be very hard for you to handle that billet. So let's say, for example, you want to have a robotic arm to grip it, but if temperature is too high, then you cannot grip it because it's too soft. It's too soft. Well, too low heating temperature leads to unmelted colorless polyhydroxide silicon paste in the slug in case of hypothetic cast aluminum alloy. So basically, if the temperature is too low, then basically the elements inside the alloy for aluminum, for example, for aluminum, the silicon paste, will coalesce, will be at one place. It's not distributed well inside the alloy, inside the billet itself. So it's very hard for you to cast materials like that. Non-uniform distributions of temperature may lead to fluctuation in solid fractions and rheological characteristics. which cause solid liquid separation during more cooling. So non-uniform. So that another issue is with the heating at this stage, non-uniform distribution of temperature. So you have to remember, you have to the billet has certain size, right? So when you heat it up, the outside layer will start to heat up first, right? Will heat up first compared to the inside. So you have to somehow make sure that the billet achieve the temperature uniformly. Temperature. So you have to give some time for the billet to achieve a uniform temperature. Heating duration has to be optimized. Too long heating time will cause structural clustering. If you heat up too long, then what happens is the structure will crossing. So the grain size will become bigger. So when the grain size bigger, then it will change the characteristic of the materials itself. So that's basically related to the question just now. Well, too short of a heating time will lead to the incomplete spheroidization of the solid particles comprising of rheological properties and leading to closing. So if it's too short of a heating time, then basically it can be hard for you to do the casting or forming. So usually the heating is done using furnace or using heater. Usually radiant electric, gas heat, or electrical inductions or resistive heater being used. The important thing is you have to make sure that part of the build is heated homogeneously, billet itself, and and for this. For example, if you use induction heater, the induction current, induction heater, so it's conditioned by working frequency of the induction heater. Usually heats up only the outer parts. So induction heater usually heat up the outer parts. So this effect is called a skin effect. Right? Then the heat from the skin will travel towards the center of the billet. So the homogenizations of the temperature of the whole part is achieved by heat conduction. So the induction current heat the outside, but it takes time for the temperature for the heat to flow by conductions to the center of the billet. So therefore, sometimes needed in order to reach the same temperature at the center of the billet. Right? Even after this time, there's a radial thermal gradient. So even no matter what happened, usually you're going to have a thermal gradient between the center and the skin of the billet. Uh, can be minimized by optimizing the temperature of the heating process with regards to the time needed for the induction heating process. So basically what it says is it's very important for you to achieve the homogeneous temperature throughout the billet. So in order to do this, basically you have to look at the temperature and also the time taken, the heating time, also the heating temperature needed. Uh, uh, so this is important. Why controlling temperature is very important because Thixoforming is carried out within a small range between the solidus and liquidus temperature. So these particular operations can happen at a very small temperature range. It should be between the solidus and liquidus temperature. So so a small variation in temperature can lead inadequate solid fractions and microstructure of the Thixoforming process. So one of the critical things of the Thixoforming process is that and it has to be done basically in a very short period of time. There are induction heating. It's being done two ways right now. Currently, normally one is vertically or horizontally heating. So this is referring to how do you place the billet. So the billet is vertical form. So you can put the billet in the vertical horizontal. And normally people use a vertical heating system, but there are some development in the horizontal. So advantage of the horizontal heating system, basically, it actually include reductions in the shape stability problem, possibility using higher liquid fractions, and alloy with a short freezing. So basically, if you the advantage of heating the billet in the horizontal form, basically, actually you can retain the shape of the billet better. So compared to if you do it in the vertical form. So if you do it in vertical form, sometimes the billet will deform itself, and basically the 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 bottom of the billet become bigger compared to the top billet. So you don't want that to happen. So you can if you do it horizontal, you can solve that particular problem. So if then basically if you do it horizontally, then you can use a higher liquid fraction. So rather than maybe 30% liquid fraction, you can go to fraction without deforming the billet, with a short freezing. For vertical type induction heating, if too much thermal energy is provided, you can have this in undesirable phenomena such as elephant foot effect and also electromagnetic hand effect. For horizontal type induction coil, the elephant foot. So this is examples of it. So this is if you heat up the billet. So this is the billet in the vertical like this. Due to the weight and due to the softness of the billet itself, you can have this elephant foot effect. But if you put it in the vertical, in the horizontal directions, then you can actually reduce the deformations of the billet. Okay. So structural evolution. So what happened during partial melting, thermal holding? So during the heating, structural evolution is controlled. So during reheating, the evolution is basically controlled in diffusion means. Uh, Holding time should be long enough to complete morphological transition from dendritic to spherical. But holding time should be short. So you have to balance the holding time between these two. So you cannot uh, you cannot it cannot be too long, it cannot be too short. So you need to optimize the reheating process uh, to achieve the most desirable slurry characteristics for the Thixoforming process. So in summary, the microstructure evolutions basically is this. One is partial remelting of the low melting point phase starting at grain boundaries. Basically, this is to determine the liquid percentage inside the pellet. So once this is done, basically there'll be a rapid coalesce of the dendritic arm, resulting in liquid entrapment. So when you heat it, so it will the melting start to happen. So basically, all the dendritic arms that's actually broken down will coalesce, will combine together, resulting in the liquid entrapment as a liquid phase. And basically, because of that, then you have spheroidic spheroidization of individual particles due atomic flux from the area of high curvature to area of low curvature. So basically, once these dendritic arms, each arm because it's broken down during the process, it becomes small. Once you heat it up, the sea is going to be coalesced, and it form the spheroidic structure of individual particles. and costing of both dissolution of a smaller particle and coalesce between particles, resulting in decrease in particle density. So basically, you have causing of both dissolutions of the smaller particles because of the heating. Some of the particles the grain structure will increase, will increase. So there's coarsening and coalescence between the particles. So, and some of the particles will combine together, resulting in decrease in particle density. So these are basically the evolution of the microstructure during that preheating process. So we covered two stages. One is how to make the billet using 4 processes, and then once you have a billet, then prior to the forming process, you preheat the billet. So during preheating the billet, you have to make sure that homogeneity of the temperature is controlled, and also the temperature is reached, and the temperature must be in between the solidus and liquidus line temperature. Okay. So the third step is the Thixoforming operation itself, the forming operation itself. Process of forming partially melted. So this is after you preheat it. So the process of forming of the partially melted non-derivative alloy slug into a near-shaped component within metal dies has been termed thixocasting, thixoforging, or in general thixoforming. So thixoforming actually represent both thixocasting and thixoforging process. The difference between the two, thixocasting is basically casting operation where you injected the semi liquid metals into the closed dies. Forging, thixoforging is basically you put it in between 2 forged molds and then you press it. Thixocasting really refers to operation injecting a slug into the slide by ram plunger in casting. So placing a slug within the open dies and squeezing 2 halves referred to thixoforging. So this is different between casting, thixocasting, and thixoforging process. But both of them are being called thixoforming process. The deformations and flow of a semi-solid alloy within the dies is a different form that to pure liquid or pure solid in either process. And in terms of thixoforming is generally preferred. So basically, deformations or flow of a semi-solid alloy within dies from the pure liquid or pure solid is generally called thixoforming process. Basically, there are 2 separate stages involving the thixoforming slug of the appropriate. So one is the heating stage we covered just now. Which is the uniform heating and partially melting of the alloy slug, which is carried out during induction heating. So basically, this is what we covered in terms of preheating. Basically, you cannot have too much of a delay time between the reheating of the billet to actually form it, either casting or forging. Right? So maximum is about 7 to 8 seconds. Because if you do that, then basically it leads to increase in solid fractions. So if you preheat it, and then after preheat you wait more than 7 to 8 seconds, then basically liquid will turn into solid. So it will decrease the solid fraction inside the billet. So you don't want that. The material flow begins with the impact of ram on the slug, and the thixoform nature of the slug allows the metal to flow into the cavity at very low pressure. So again, I mentioned just now, thixotrophic materials, it will whenever when you don't have any shear stress, it'll maintain its shape. But if you apply shear, then basically the viscosity will go down. That's what it says here. So material flow with the impact of RAM on the slab. Uh, because of the nature of thixotrophic materials, basically once it's a shear, then the viscosity will reduce. So because of that, the metal can flow into the cavity at a very low pressure. At the end of the forming stroke, the pressure increases to the selected level to form fully dense components. So at the end of the stroke, only then the pressure will increase. Make sure that to make sure that you have a full dense component. Time of containment under pressure depends on the alloy and part dimensions, and it's normally only a few seconds in duration. So the holding time after the forging or casting is only a few seconds. And you can this depends on the heat transfer, big transfer to the die. So if if uh, if, uh, if if the heat transfer being transferred to die efficiently, then basically you can cut down the holding time inside the mold die. Horizontal heating arrangement tends to operate with liquid pressure around 0.6, vertical with 0.4. So again, during the heating of the materials, right? If you do it vertically compared to horizontally, so if you did horizontally, you can achieve liquid fractions about 0.6%. And if you do it vertically, you can only achieve 0.4%. If you go beyond that, then basically the billet will deform. So this is examples of Thixoforming machines. So you have ramp move up. So this is the pellet being placed in there. So this is in terms of forging. So this is examples of the RAM semi-solid. So you push the semi-solid materials inside here, and this is die box to form the whatever product that you want to make. So the forming process itself requires a extremely low punch force at the beginning of the forging process, because, as mentioned, thixotrophic materials will have a very low viscosity once you apply pressure on it, when you apply stress on it. A punch velocity should be as high as possible in order to close the die as fast as possible. So basically, the punch velocity, the velocity of the plunger, should be as high possible in order to close the die as close as possible. So you want to make sure that this operation can be done as fast as possible. Because the difference in temperature of the materials and die causes quick cooling of the workpiece. So you have to do it fast, because when the material is in contact with the mold die, right, then basically the heat transfer will be done, will happen rapidly. So you don't want it to be cooled too fast, because if it's cooled too fast, then the viscosity will go up. That's one of the reasons. The other reason, because you want to keep the cycle time short for productivity. But you have to make sure that when you